All we wanted to do was to make a film about British lighting industries. But they said we couldn't possibly just make a factory film. We had to have human interest, they said.
Hey, what's going on? I'm trying to get some sleep.
Ah, good morning. We were wondering if you'd tell us what artificial light means to you.
What, at this time in the morning?
Especially at this time in the morning, before dawn, artificial light, get it?
What's that got to do with me?
You're supposed to show some interest in the subject. For instance, what you know about that electric light bulb you've got there.
What do I know? Well, it lights. What more do I want to know?
I don't know what else you want to know, but we're going to tell you how we make them.
Okay, go ahead and tell me. I might as well get up anyway.
Right, well, we make light bulbs in all sizes, from 25 watts to 1500 watts. We call them incandescents because they make light by heating a filament. So let's start there, with a hair-like piece of metal that operates at a white heat and won't melt whilst it does so. We make 6 million a week, including 1.5 million braided cathodes, which are a special sort of filament used in fluorescent tubes. Filaments are coils, and their manufacture requires a high degree of precision and control. Now, these machines, designed and manufactured by the company, achieve this precision and run at speeds of 10 to 12,000 revs per minute. Coils and coils made from coils. They're wound on a mandrel wire. After cleaning in an annealing furnace, they're cut to the required length at the rate of 8,000 per hour, and the mandrel is dissolved away, leaving the finished coil. But before the filament is ready for use, it must be checked by the inspection department, and checked again by quality control. And then they're fed into the machines that make the finished light bulb. Watch. British lighting industry lamps are guaranteed for 1,000 hours and are tested to comply with the British standard specification. During production, each lamp is subjected to 8 separate tests, not only to ensure its electrical quality, but also its mechanical ruggedness. But another sort of lamp is brightening modern life. We got another bit of human interest in here. I ought to warn you, he wasn't too keen on the idea when we put it to him, and still, I hope they've persuaded him.
Oh, you can have a go at me now, then.
Well, no, not you personally. I just wanted to use you to introduce fluorescent lighting.
Do lay off. Yeah, pass us that tube.
Look, if you're not ready, we can come back.
So.
Well, it's jolly decent of him to do it at all, really. It's not as if he were an electrician. He's just a rather angry young man.
Right, put that switch on.
I'm not quite sure what these young chaps are so angry about.
Satisfied?
Yes. What a charming fellow. Well, now, where were we? Oh, yes, fluorescent lighting. Well, most of us spend a good deal of our working day under fluorescent lighting. Modern offices, showrooms and factories make extensive use of it because it gives a high efficiency in terms of more light for the same electrical consumption. British lighting industries make tubes from 6 inches to 8 feet long in the order of 250 miles per week. Every hour, samples are sent from the production lines to the photometry section. Here, their light output is measured against a standard reference tube. Each one is connected to the same control gear so that the only varying factor is the tube itself. Any departure from standard is registered by a sensitive galvanometer at the control position. Yet, the final judgment must be made on a tube in its fitting, because its efficiency depends on the quality of the tube, the control gear, the circuit, in fact, the whole fitting. British Lighting Industries make control gear in a factory in the north of England. Over 18.5 million units are made in the factory each year, and more than 1,000 operators are engaged on their production. The main part of the control gear is a choke consisting of a coil of copper wire and a former. First, a few turns are wound and taped down, and then the machine automatically winds the required number of turns for each type of coil. 2,500 tons of copper wire go through these machines in a year. These sticks consist of several coils end on, and are subsequently cut into single units and the ends secured and finished. Finally, the laminations are inserted and the choke is complete. This 65-watt choke represents a considerable part of the factory output, and it will find its way into one of the super slim popular pack range of fittings. These have been made in another factory on this site. The output of fluorescent fittings has recently been enormously increased by another British Lighting Industries development. This machine accepts sheet steel from a roll at one end, shapes it longitudinally, cuts it, and delivers a completely formed spine at the other end. As we said, the fitting is more than a support for the tube. It's a scientifically designed unit which takes into account the light distribution and heat dissipation, as well as housing the tube and its ballast. Fluorescent light fittings have to form part of lighting schemes but differ widely, so they have to be produced in a large range of sizes and light outputs. They may be used to light a factory or to floodlight a cathedral, department stores or dairies, co-stores or concert halls, bowling alleys or boardrooms. If you keep your eyes open, you'll see fluorescent fittings practically everywhere you go, and there's more than an even chance that they will have been made by British Lighting Industries. If you follow the fashion magazines, the colour supplements or such like glosses, you will have realised that photographers get their models into some pretty peculiar positions these days. But it's the lighting they use when they get them there that's interesting.
Well, I must say that's a new approach.
No, I mean, well, you see, this is a film about lighting, and that light they're using on you is a fairly new type. I'd like to say a few words about it.
Oh, won't that be rather a bore, though?
No, not really. You may be surprised.
Well, I'm absolutely trapped here, as you can see. They take hours. So do carry on. I mean, what can I lose?
Well, nothing, I hope. If you want to reduce the size of high-powered tungsten lamps, you'll have problems to face. A filament disintegrates slowly under high burning temperatures, and the waste products of that disintegration will blacken the glass wall. So they had to use massive filaments and big envelopes in order that the blackening should be spread over a large surface area. If some way of reducing the disintegration could be found, the two problems would be solved at once. The filament would withstand higher temperatures, and the bulb would be made smaller. They found the answer in a chemical that once came from the seaside, iodine. But let's start at the beginning. The tungsten iodine lamp starts life like any other incandescent, with a filament, except that it is supported in a quartz envelope hardly larger than it is itself. Now this is sealed at both ends. Through an exhaust tube, iodine crystals are introduced, and this iodine collects the disintegrating particles at the inner surfaces of the quartz envelope and carries them back to the filament, thus increasing its life and keeping the quartz clean. Of course, it's not quite as simple as that, but for you and me, that's what it amounts to. The technical boys will tell you much more about the tungsten iodine cycle, about stabilizing in dry hydrogen, flushing with argon, degreasing, and several more highly complicated terms, all of which meant that when these lamps were being produced under experimental conditions, it all looked a bit like a witch's cauldron. But today, the tungsten iodine lamp, which British lighting industries pioneered in Europe, is the modern answer to floodlighting, and for those problems where a large punch of light is needed. A pencil-slim tube that allows the size of fittings to be reduced and at the same time gives twice the life of the ordinary bulb. The story of production in British lighting industries covers a lot of ground in every sense because their factories are pretty well spread from South Wales to Durham. But behind this story lies another which is of great importance for the future: research. There are three aspects of research that concern the lighting man: distribution, efficiency, and color. Take light distribution first. Sometimes it's necessary to direct light accurately. This tungsten iodine fitting is designed for applications where the shape of its beam is very important. The angular distribution of its light can be studied on this instrument, where a photoelectric cell is mounted at the end of a long tunnel. By rotating the fitting relative to the photoelectric cell, its light output can be measured at every angle. And this is of great importance for floodlighting, or on a smaller scale for exhibition or shop display work. Light distribution is vital on the roads where the motorist and the pedestrian depend on modern street lighting. In this field, British lighting industries have made important contributions. The problem is to make the available light do the maximum amount of good, but without glare. This means the right light in the right lantern. Now, these lanterns are optically designed to very exacting specifications. They put their light where it is wanted, on the road, and not in the motorist's eyes. They're designed not only for performance, in the sense of light distribution, but also performance in the sense of efficiency, trouble-free service in all the rigors of our British weather. So we give them extensive weathering tests, and as if there wasn't enough rain about, we make our own to test them with. Street lighting also provides us with an example of the second of our research questions: efficiency. In this case, what you get in the way of light in return for the money you spend on electricity. Tungsten lighting gave about 15 lumens of light per watt of electricity. Then we had discharge lamps and fluorescent tubes, which improved things a lot. But the real breakthrough in street lighting came when, at Leicester, they developed the 200-watt linear sodium lamp, which gave 20,000 lumens of light. And in case your arithmetic is as bad as mine, let me point out that that means 100 lumens per watt. This was a very high conversion of electrical energy into light and revolutionized street lighting practice, and the figure is being constantly improved. Whilst we're still on the street, so to speak, there's another sort of efficiency that's important to the consumer, in this case the motorist. In modern motoring, the stresses on vehicle lighting increase. The mechanical shocks suffered by headlamps on the roads are recorded on tape by special test cars, and these recordings are then used to reproduce the vibrations on a special rig in the laboratory. Here, the behavior of filaments and supports can be seen under a stroboscope, and any dangerous frequencies recorded and investigated. We've spoken of light distribution and efficiency. What about color? What color is this? Red or blue? It's all a question of the color of the light, and that's a question of fluorescent phosphors. These phosphors glow under ultraviolet radiation, and that's really what happens in a fluorescent tube. The color of their light will depend on the mixture of phosphors used to coat the inside of the tube. These new fluorescent phosphor mixtures were all developed in the chemical research laboratories of British Lighting Industries. The results of such developments may be seen in the color comparator. On the left, the patterns of cloth are lit by a fluorescent tube emitting most of its light from the blue end of the spectrum, while on the right, they're lit by a warmer color. Fluorescent tubes such as this, enhancing the reds and yellows, are installed in some of the largest supermarkets, so making the product especially attractive to the customer. But the fluorescent tube has a whole field of research to itself, increasingly being accepted both for industry and in the home. Its efficiency and burning characteristics are a matter of constant development. In the laboratories, this photometer has had to apply the methods of mass production to research. It measures total light output and gives a record of each lamp so that the results of experiment can be quickly verified. A fluorescent tube is at its most efficient within a fairly restricted range of operating temperature. To investigate the behavior of a tube under wide temperature variations, a typical research tool was evolved. The results of such investigations as this have widened the area of application of fluorescent lighting so that they can now be used in cold stores or the tropics. Today's problems are complex enough. Tomorrow's will be more so. If we're to have a chance of answering them, we must have the resources of such companies as British Lighting Industries to foot the bill for research and development. Light, artificial light, we take for granted, and so we should. But as you switch your light on, try not to forget one thing. British Lighting Industries is the research and production organization behind three trade names: Atlas, Echo, and Mazda. And that's a tip worth having if you're interested in light.